the video's already up for yesterday's talk. He's asked us to embargo his video for a week. On archive, so I don't know if you that video won't be up tomorrow, but Philip's talk is, he doesn't really, well, I just sort of told him, so maybe he does know this now, is last time he was here, I was also talking after him, and this talk has a load of demos in it. And then traditionally what happens with this talk is I dig out the talk. Shall we do this? Shall we help them? No. What happened, as often happens when you're trying to give a talk after the person before, is that I was busy trying to fix all the demos to get them to work during Philip's talk, and I missed sections of what he said, so I got him to come and give it again. So I had the same problem again. I was up quite early this morning trying to fix the demos and realized it was going to be quite a lot of work, and I sort of thought, I'll not bother then. So apologies. There are normally more demos in this talk, but this time I wasn't going to, well, I will invite Philip for the third time to do this, but I thought I really needed to not sit there doing extra preparation during Philip's talk, because certainly I really enjoyed that talk, and I definitely wanted to see it. So, context to what I'm going to talk about. I guess this sort of dates back to, I've always had this, one way I got into Gaussian processes. Well, two ways. One was trying to understand what the support vector machine was and what the equivalent sparse algorithm would be for Gaussian processes, which is something called, which we did call the informative vector machine, which we haven't talked about at all. But then I was also interested in dimensionality reduction, which I'm going to sort of motivate in a moment. And this talk is really about how it turns out. So Gaussian processes, at the time when I sort of did this work, were known to be supervised learning algorithms. You could do classification and regression. But this sort of work shows how you can also use them to be unsupervised learning algorithms. I mean, we know Gaussians are unsupervised learning, but Gaussian processes can be too. So I suppose, my first sort of main interest when I was a PhD student, it wasn't really my thesis work, but what I thought was a really important challenge was nonlinear dimensionality reduction. So the motivation why I thought it was a challenge was because of this, that we get these very high dimensional data sets, and if you sort of sample, if you have a model that says, well, we'll switch on, this is a 64 rows by 57 columns. We have a model that says we'll switch on randomly pixels in this image with the probability they're there. Then you can sort of sample things that look like that. And the space contains a lot more than that digit. And actually, it turns out that even if you sample every nanosecond from now until the end of the universe, you won't see the original 6. There's another sample, that's proof by example. That wasn't the original 6. So that space is massive, it's just an enormous space. 2 to the 3,648 possible things in that space. So modeling directly in that space seems like a very bad idea. Now the idea with dimensionality reduction is something like this. So here's a simple alternative model of the digit. Let's forget about the representation we're given, and let's just say we could rotate a prototype digit. So here's a model that covers the digit 6. So we can say all 6s are generated by taking a template 6 and rotating it, which I think seems reasonable. So it turns out, that would have been a demo there, but turns out that if we do that, if we take the digit 6 and we rotate it, I think the original 6 is up here, and we rotate it 360 times to build the data set. And then we do principal component analysis on the data set, and we look at the first 2 principal components. So that's a linear projection of the data, the linear projection of the largest variance, although I don't like that interpretation. it's a fine interpretation, but I don't think you should associate with PCA. You see this circle. And what you see is this slightly weird characteristic that I always say this and I've never checked, but I'll just keep saying it as if it's true. I think that you see this little bit of extra noise on this circle here. There's noise on the circle in general, and the noise is coming from the fact that when you rotate a digit, it's obviously you're rotating pixels, so they only rotate correctly at 90 degrees, 180, 360. And I think when you're very close to that rotation, the bilinear interpolation you get is particularly nasty. So you get a little bit of noise around here and noise everywhere, but basically what you see is a one-dimensional structure that lives in this 3,648 dimensional space. So your data that we've artificially generated is one-dimensional. It's not 2 to 3,648 dimensional. And you might say, if you say, well, those weren't 6s, some of them were 9s. Yeah, sure. So here's the 9s and here's the 6s. And one thought that I sort of definitely used to be on my main way of thinking about data. I think there's flaws with this being the only way, but I think it's a good way of thinking about lots of data, is that maybe all data is just some template example, like the average man, and then distort the average man in various different ways. But you can't represent it quite like that because there's sort of clustering, so there's several average men. You have several means, and then people are disturbed away from those means. I think people like that idea. They sort of like mixes of Gaussians, and somehow that might seem to represent it. But of course, pure rotation is too simple. The distortion of these template objects should probably be a little bit more than that. So digits, for example, undergo thinning, so their stroke becoming thinner and they stay digits. They undergo translation, and there's other transformations. 7s can have cross bits appear and disappear, and all these items stay as original digits. But the argument is very often that, and I always say, if this isn't true, I think the data's almost uninteresting. For any data with what loose term structure, we expect fewer distortions than dimensions. So we expect the data to live on a lower dimensional manifold. I kind of even would argue if this isn't the case, then someone's just given you, and you're trying to model this data, someone's tricked you, they're giving you noise. If all those pixels are genuinely independent, so people talk a lot about the curse of dimensionality, and I have a controversial but correct view. That it doesn't exist. It's a sort of mode of the way you're modeling your data. I mean, all analyses of it doesn't exist in the data, it exists in your model. You can create models that exhibit the curse of dimensionality by assuming independence, but that's just a dumb thing to do. The thing that does exhibit the curse of dimensionality is true independent noise. So if this doesn't happen in your data, I would argue that you've just been given true independent noise, which probably in itself is a pretty rare thing. So I'm sort of defining my way. I'm saying all real data has this characteristic by some way. But these are just claims. Obviously, I like to be controversial, so you can disagree if you like. Notation. So this is the same sort of notation I've been using so far, but it's worth revisiting it because it will come out in the maths again when I go through some of the derivations. Our data y is what we're observing. Now we're going to do latent variable modeling, and some people, when they do latent variable, they like to observe x and have z as a latent variable. Because I like the fact that it's actually all a regression problem, I like to observe y and have x as a latent variable. So x, which was our inputs, is now a latent variable, and hopefully that'll become clear why. The data is again in this design matrix, which becomes really important when we start looking at some of the structures that emerge in the derivation. So the data has n rows and p columns. And actually, I'm typically going to work with centered data for convenience. You don't have to, but it just makes the notation cleaner and makes very little difference for the derivations I've got. So the centered data is y hat. And it's just the data with its mean removed. Latent variables have exactly the same shape of matrix, apart from they've got q columns. So the latent dimensionality that we're looking for is q. So q-dimensional latent space. And in the linear case, that gives us a mapping matrix that maps from, with an affine transformation. This is a sort of linear dimensionality reduction. From the latent space Q to our observed space P, I'm going to use W, which is machine learners use for regression weights instead of beta. Beta's a bad thing to use because it's difficult to turn into a matrix. It just becomes the matrix B, and then it confuses with a load of things. So that's my claim why W is a good thing to use. But beta would be the equivalent if you don't like. But it's a matrix. It's a sort of, because we'll be doing multivariate Gaussians. Oh, and then I always use this little MATLAB shorthand. So AI colon is a vector from the ith row of the matrix, and A colon J, I've been using that before, is a vector from the jth column. So this is a vector of features associated with the ith data point, and this is all data points, the feature value of the jth feature. Okay. So the reason why that notation is a little bit important here is that this is not a normal way of what I want you to start getting used to is seeing that and recognizing that as the sample covariance. So by that definition, y hat transpose y, because y is centered, is the sample covariance. The inner product, which is what we've been obviously looking at with covariance functions, is y transpose. So that's an inner product matrix as we think of it. So this is a P by P matrix, and this is an N by N matrix. This is the sort of thing you use for a linear covariance function. If your input data was Y, normally we've been saying XX transpose. But the same thing would apply to XX transpose. So, because it's going to appear in some of the little bit of maths that will come in. So in linear dimensionality reduction, the idea is we have our data in some Y space on the right there, and it's being mapped from some latent space. So these are the two sort of things that we think we're varying, like the rotation on one direction, we might be varying the rotation, the other one thinning. Of course, it doesn't work here because it's a nonlinear relationship, but that's the idea. You've got some sort of, so when I explain this to sort of non-technical people, I try and explain, well, it's all like puppetry. The puppeteer is just putting two signals in, and you're observing a high-dimensional puppet moving around, high-dimensional response. So this is what the puppeteer puts in, and that's what we observe in a three-dimensional space. So it's mapping a sort of plane. It defines a plane. But if we're going to do it probabilistically, we also have error. So we sort of say it defines a plane. Sorry, I've absorbed that mu. I'm absorbing that mu in by centering my data. So I'm just going to say y is equal to wx plus some noise, where the noise is Gaussian distributed with some variance. So of course you sort of see that I'm defining that in effect in a very similar way to the way I define linear regression. But what you do next is kind of traditionally different. Latent variable models, I mean, I think they're more in the sort of social sciences and psychology. Factor analysis was the sort of first example of people doing this. And what people were trying to do was understand if there were latent sort of factors behind people's intelligence, things like IQ or things going on in society. And they were sort of there, I think, before any other group of people. And there's a bit of a story behind why PCA exists, because it's actually invented as a factor analysis method, which is why I think, again, this separation between model and algorithm is important. And it's invented in very much this way. If you read Hertelling's paper on PCA, where he invents the name, this is sort of the thing he describes. It's slightly different here. This is probabilistic PCA because we've got the noise in. Hertelling didn't put the noise in. So the idea is you have a linear Gaussian relationship between your latent variables and your data. So you're mapping from some unobserved x to y. And to deal with the fact that x is unobserved, I should just get one of these. Which one of these is the right one? This one. Yeah. OK, I'll see if I can do better than Philip did in that way. I'll put that one over there. So in the standard latent variable approach, you deal with these fact that these guys are missing, these x's, you don't get to observe them, in the obvious sort of way. And I think there's no controversy about this amongst frequentists and Bayesians, because there's no issue of that being a parameter. That's considered a variable. You define a Gaussian prior over that space x. And that gives you a marginal likelihood of this form. Now this proof, I followed through this proof, and it's quite a long, it's not that bad, but it involves Sherman, Morris, and Woodbury inversion to show what happens here. But we'll redo that proof using those multivariate properties in a moment. Because, as I hope you'll see, this is the beauty of linear Gaussian models, all we've done is define Gaussian, and then we've mapped it linearly. So this should, now you should be getting to the state where that's obvious. That will clearly be the covariance of the marginal. And this is why. Because we're just saying that x is Gaussian distributed, and epsilon's Gaussian distributed. And if x is Gaussian distributed, we know y must be Gaussian distributed. So this is the ith data point x. The ith data point y must be Gaussian distributed, and it must have this covariance. Yeah, that's the standard rule we keep looking at, W transpose. So that's the, well, sorry, that's not y, that's kind of f. That's like the intermediary f, the noiseless y. And then if we add noise, sum of two Gaussians, both zero mean, the new covariance is the sum of their covariances. This is what I'm saying, this is why these things are interpretability. There's one part, which is this low rank part, and these low rank parts always have this interpretation of some sort of reduced number of variables that we're mapping out. Remember, they came up in the sparse Gaussian process stuff as well, a low rank part. In that case, the interpretation was these inducing variables, and those inducing variables had a particular prior, which was non-spherical, but we got shapes like this coming out again. Yeah? So these shapes keep appearing, and when they appear, it means what you're doing is you're controlling things with a reduced number of variables. So if you've got the full rank, of course that comes up in fixed basis function models. You're controlling things with a reduced number of variables, which is W in the fixed basis function models. So that's why these things keep appearing, and they appear again here, low rank part plus noise. And that's the factor analysis type interpretation of PCA. How do things differ in factor analysis as we understand it? In general factor analysis, this noise varies for each output dimension. So the noise is diagonal. So general factor analysis, which isn't PCA, has a diagonal noise there instead of just a spherical noise. That's the only difference between the two models. Algorithmically, things go in a different way. So the story behind PCA, if you read Hertelling, he talks about the social scientists and factor analysis, and then he says, oh, but factor's not a good name because it means something in mathematics. So I want to call this principal component analysis. Worst decision ever. It's a factor. It's a factor of the covariance. So it's true that the social scientists were intending factor to mean something different, like the factors that are affecting the way your life evolves, but actually it's still, he calls these the components, but they're factors. It's a decomposition of the covariance. In fact, he didn't even have this spherical term because it's just a decomposition of the covariance. So this is all factor analysis, and it was just a renaming. People then credit it to Pearson, but Pearson was talking about a totally different thing. The algorithm turns out to be the same. Pearson was talking about regressing between two variables. If you regress x to y, you get something asymmetric from if you regress y to x. And he said, let's try and find something that's symmetric. Coincidentally, the algorithm for solving that is the same. The model is different. Importantly, though, if you try and non-linearize what he said, you would get a very different answer from non-linearizing this. This is when it becomes difficult. So what's nonlinear PCA? I want to make this algorithm nonlinear. It depends which interpretation I start with as to what nonlinear model I come up with. So there's like 19 different ways of doing PCA in a nonlinear way. It's just this is the correct one. Okay. Those are jokes, by the way. I'm not. Okay. So this. Once you get to that point, so Hertelling realized that without this diagonal noise, that this system was solvable by an eigenvalue problem. What Mike Tipping and Chris Bishop did in their 99 paper, and I was at Aston around the time Mike was working on this, so this is big influence on me, and I knew Mike very well, still do, was they proved what the maximum likelihood solution for this is. And it's sort of non-trivial because you have to do a bit of a substitution with a singular value decomposition. But the result comes out like this: that if this is your probability of y given w with this covariance structure here, C, this is your log likelihood, and we've used this trace form, which is quite useful sometimes for these multivariate things, but this is just the standard Gaussian log likelihood written in this trace way. And it turns out that the maximum likelihood for W is found based on this. If I take UQ to be the first Q principal eigenvectors of this, and the corresponding eigenvalues are lambda Q, then this is the maximum likelihood solution for that model. So W is given by the eigenvectors times the not quite the eigenvalues. This is the square root of the eigenvalues minus the variance, the noise term. This is really important, very interpretable. And if you think about things in this way, a lot of PCA stuff becomes clearer. I'll mention something about that briefly. Times an arbitrary rotation. Why is there an arbitrary rotation? Because it's appearing inside here as R transpose R. So all that stuff that everyone tells you that, oh, principal components are up to a rotation, they're not defined, all this sort of stuff, I think it's much clearer when you understand the model and what the, and it is Hotelling's model as well, broadly speaking. So what's going on the eigenvalues? Well, you know when you do PCA, you know the mythical elbow plot, yeah? So if you read textbooks on PCA, they say, how many latent dimensions do you record? And then they say you plot your eigenvalues, and then your eigenvalues, they always have this elbow for all data. And then what you do is you say, well, this is just the residual eigenvalue, it's the noise. And then you retain these ones above the elbow. So you look for this elbow. Of course, in practice, the elbow doesn't ever really exist unless you generate from that eigenvalue spectrum. But it's formalized here really nicely. That is the noise, sigma squared. So that's this little bit here, sigma squared. And it's saying that W, you remove that spherical term. What that means in terms of, you know, we talked about Gaussian covariances before, and I said the way I like to think of Gaussian covariances is through a basis, all we're doing is rediscovering that basis, right? So the eigenvalue decomposition of the covariance is just trying to find that basis, and this sigma squared term that is being subtracted off actually just adds a bubble to this basis. So if the sigma squared gets too large, if the noise, what this means in practice, okay, you sort of think, well, what happens if sigma squared is larger than an eigenvalue? Well, if you fit this model by starting by fixing sigma squared, and once you fix sigma squared, you then proceed as normal, then you only retain eigenvalues that are larger than sigma squared. So in some sense, if you know sigma squared, this is exactly what everyone's telling you with the elbow plot. If you know sigma squared, but they don't do it as nice and elegantly as this, I think. If you know sigma squared, your noise, what you're saying is for creating your principal components, you should throw away all eigenvectors with eigenvalues that are smaller than the noise. Yeah? So you only keep ones where the eigenvalue's larger than the noise. If you fit the noise, you can't fit the noise and the dimensionality. If you fit the noise, what it turns out is the maximum likelihood solution for the noise is just average of the discarded eigenvalues, as you might expect. Okay? Is that clear? That's nice, and that's nothing to do with me or Gaussian processes, but it leads. Well, it is. I mean, these are sort of Gaussian models. Philip did it. I'm doing it too. But it does lead to something else. So I was kind of very aware of this work, and as a sort of early career PhD student, Mike was a postdoc, and he was doing this stuff, and I was kind of slightly in awe of that and Gaussian processes and everything else. I was at Aston. It was an amazing place to be then. Still is, probably. Nonlinear dimensionality reduction. Okay, so now we want to do something slightly different, because we don't believe in that linear assumption, and what we want to do is make this mapping in a nonlinear way. But it's problematic. Okay, so what happens is we propagate, so it works nicely to take a Gaussian and propagate a Gaussian through a linear function, because it stays Gaussian. That's the entire reason we're sort of here. As people have said, you could even use that to derive Gaussian processes, or to define Gaussian processes, I should say. But if you put a Gaussian density on these things here, if you treat them with any probability density, unless you're very careful about your choice, and then you do a nonlinear mapping, what you'll find is you get an intractable probability distribution on the right. So it's easy to sample from, but it's very difficult to normalize. So, I mean, you could think of in one dimension we're mapping, this is actually a bit like the curve thing that Philip talked about, but in this case you don't know x, you don't know, you've got some curve in the two-dimensional space, but you don't know the location of these values on here. I mean, it's quite a general thing. Even if you do it in one dimension, right, you can get quite funky non-Gaussian, multimodal. It's a very general thing to do to a probability distribution. Take it through a nonlinear mapping. It gives you any other probability distribution, kind of. So here, in order to do this one, I sort of have normalized it, but I did a bunch. It's basically done through a kernel mapping a bunch. This isn't really a Gaussian. It's a whole load of Gaussians sat on top of each other to look like a Gaussian that are then mapped out. So what people have done in the past is they've done sampling. So they come up with a grid-based representation of X. There's some really nice work by David Mackay, which again was around the time sort of 96, 97. I think he talked about it, Aston, called called density networks, which also leads to another work called the generative topographic mapping. But I don't really want to talk about that. It was how I got into it. But I want to go back to this point here and say, well, we're defining these models. From a sort of Bayesian's perspective, W is a set of parameters, and you really want to integrate out the set of parameters. So it caused me to ask the question, well, integrating out the variables, if you have a perspective that everything's probabilistic, is just as bad as integrating out W. You know, if you want to integrate out, if you can't, what happens in practice is once you've got this marginal likelihood back here, you can no longer do the integration to integrate out W. So if you're Bayesian, if you now want to sort of, you can do this by maximum likelihood, but if you want to integrate out W, it's not tractable. You'd have to turn to sampling or approximations for that. But if you go to this part of the model, you say, well, at this stage, why should I integrate out the missing values? Why don't I integrate out W, the parameters? And you can do exactly the same thing. You can define a Gaussian prior on the parameters W, and then you get this interesting alternative distribution. There's a few interesting things about it. So what we're saying now is, this is our model. All I'm doing now is I'm writing Y as a column instead of Y as a row of my design matrix. And that causes the roles of X and W to sort of flip. So where we had X from W before, so there's this duality because W and X always appear as an inner product. It's totally symmetric in this model. And when you put a prior distribution over W, then and you add noise, then you can show that this thing, which is actually the sort of F value for all data points, but a particular feature, is distributed as a Gaussian with this covariance. And if you add the noise in, you get that covariance plus sigma squared I. So I see a couple of people nodding. So I hope you recognize what that is. But that's, what is it? Everyone together? No? Yeah, that's it's a Gaussian process with a linear covariance. What's interesting about it is a multivariate Gaussian process, because Y is of course multivariate, but it's one that's independent across P. And that's not clear on this thing, but I'm showing it here. Because this prior distribution is independent across P. I've written the independence here across N, but it's actually independent across P and N. And if I rewrote it as Y given capital X W, I could make clear the independence on P. I mean, it's independent in everything. It only becomes correlated when you integrate out W. So we get this independent model, which is a series of Gaussian processes. So the new model is that what we're trying to do, and actually now X is going to be our parameters, we're going to optimize with respect to X. So instead of doing what sort of Hotelling was doing, and Mike and Chris, what we're now doing is we're saying, what I've got is I've got a bunch of Bayesian linear regression models, which is what this sort of Gaussian process is, and I've got a bunch of output, and I'm going to try and find the inputs that best describe those outputs. Yeah? So that's what I'm doing now. Instead of trying to find the parameters, I've integrated over the parameters, but I'm going to try and define the inputs that best describe those outputs. Now, I got into this, I had the idea for this model without going through this, to be fair. And I did this proof on the night before submitting the paper, because I sort of thought, oh, a good way of illustrating the paper would be to go through the linear case. And this is like the only serious proof I may have ever done, and it was the easiest proof ever, because this is the likelihood where I'm using K to represent this covariance function. And this is the solution, that U prime Q are the first Q principal eigenvectors of 1 over P y transpose, where that's the inner product matrix of the data, not the covariance matrix. The corresponding eigenvalues are lambda q. But other than that u prime, the whole thing has a familiar air to it. And I was embarrassingly about halfway through the proof, or maybe even completed, before I sort of noticed that if you just do that, you see the two proofs are kind of exactly the same. And I had Mike and Chris's paper in front of me. So all you do is replace the x's everywhere with w's, the y's with y transpose, the n's with p's, and it comes out. Because of this weird dualities, and PCA is really weird because of these sort of, all these, it's the optimal linear Gaussian and all this sort of stuff. And so much stuff comes back to PCA, and it turns out this does as well. So this is the solution for probabilistic PCA. It's this eigenvalue problem on the covariance matrix, and this is the new solution. It's the eigenvalue problem on the inner product matrix. But these eigenvalue problems are sort of equivalent. The equivalence is UQ, the eigenvectors of the covariance, are given by y transpose u prime q, the eigenvectors of the inner product matrix, times this negative square root of the eigenvalues. This is very well known in statistics, where people, if they're doing PCA and they have more sort of features than data points, this is the more efficient eigenvalue problem to solve. But it's sometimes called principal coordinate analysis, and it's also known as classical multidimensional scaling. It's a sort of scaling method because, in common with scaling methods, you're solving for x, not solving for the mapping. And that's what people tend to do in scaling dimensionality reduction, which are a very interesting class of methods. And this particular variant turns out to be equivalent to probabilistic PCA. So I sort of called it dual probabilistic PCA at the time, but maybe a better name would have been probabilistic principal coordinate analysis or something like that. Because all you're doing, this is solving the same thing. I mean, these are different models, but the algorithm turns out to be the same, or the algorithm leads to the same answers or equivalent answers, but this algorithm is solving for x, and this algorithm is solving for w. So again, this weird thing, we've got two different models, the algorithm is kind of the same. But the point about this model is this is much easier to non-linearize, because all we now need to do is replace that linear covariance with a non-linear covariance. So we can just put any of the covariance functions in there we like and optimize with respect to x. So there's some funny things going on here which are probably worth highlighting. That I love this way of defining a model. That this really turns a lot of traditional statistics on its head, because we started off by defining, if you think, well, certainly parametric statistics, we've defined a model that's independent across P. So have you ever heard of the large P small n problem? Yeah, I mean, it doesn't exist, actually. It's a consequence of medical definition, and this is provably the case, because this model has a small p large n problem. Because it's defined independently across P, if you want to prove the consistency of the maximum likelihood for this model, you need to show that you can't prove it for increasing data points, because every time you add data points, you add parameters, and they never become better determined. So you have to show, the way you can show the consistency of the model is for increasing data features. Every time you add a data feature, your understanding these x's becomes better determined. So this model has a large n small p problem. So it's a consequence of model definition. In particular, it's a consequence of how you've expressed your correlations, this is why now you see I'm so obsessive about let's express correlations between everything, because these problems start to arise when you make these independence assumptions and you appeal to these traditional frameworks about parametric models. And in that, if you do that for this, it sort of all falls apart. You have to turn everything on its head and say, oh, well, I can show that this model will converge to the true model as the number of features I'm given increases to infinity if the number of data points I'm given stays the same, which is totally the opposite to what everyone normally expects. And the fact that that exists, and it's just a consequence of how we've chosen to define a model, shows you that these problems perhaps aren't as serious, aren't fundamental, they're to do with model definition. I mean, I don't want to trivialize them, they do exist for certain models, but they're a consequence of your model definition, not anything fundamental in the data. That's why our motto, prior is king. It's all about the model, it's not about the data. So curse of dimensionality is a consequence of your model, not your data. So this is a product of Gaussian processes with linear kernels, and so the idea is to replace this with the exponentiated quadratic or whatever covariance function you like. Of course, that means you can no longer solve x with respect to an eigenvalue problem. You have to do a large nonlinear optimization using conjugate gradients, BFGS, or I think we often use these scale conjugate gradients thing, which would be interesting to know. I've never studied it. It'd be interesting to look at it in the context of the picture that Philip just portrayed. So a little bit, one thing that's worth pointing out here is, again, we're just doing this, we're doing what we often do. We've got a K, we're just fitting Gaussian models, but the K is not a regular covariance. It's not free to do anything it likes. It has to, is parameterized by kernel parameters, and what we're now doing is we're saying the x are like additional kernel parameters. So in order to fit this thing, you need to take the gradients with respect to x and do optimization with respect to x as well. So what you're getting the ability to do is sort of move around data points. If something is correlated on the output, and we're using exponentiated quadratic, so you're seeing two things are correlated, sort of item 2 and item 1, what you're trying to do in the latent space is move those things closer together. It's a little bit like scaling methods try and do that, but they don't have such complex things, and they often don't have models underneath anything. But a lot of multidimensional scaling iterative methods have something like this going on. Okay, so there's a few, this is the point at which I was supposed to sort of show demos, but there's a really nice, I should have found this before. Let's see. It's nicer to show other people's work, because that's sort of my work, and but people have used this model in anger, and I'm going to try and find my favorite example of them doing that. Here we go. This was a 2006 paper. This guy, Bill Baxter, he took my code and rewrote. Well, I wrote it in C, and he took my C code, C++. He took my C++ version and actually wrote it in. Oh, there's the Vimeo. Oh, I need to search for Vimeo. Can anyone see a link to Vimeo? It's a bit hard from this parallax. No. No. Oh, there we go. Oh, good. I thought that was the same thing. Okay, here we go. So, it's great. Release your code online. It's fantastic. Bill took the code. It wasn't BSD licensed, the code. GPy is all BSD licensed, so anyone can do anything with it they like. He was working in Japan or something. He's on animation. I've never met this guy. And he fixed a load of bugs in the C++ and gave it back. But he used the code to do this, which was a Eurographics paper. And I think this is a super surprising, and I think it's a consequence of the model. The fact it is surprising that you can do what he does here. So there's some complexities to this, but what's basically going on, and the complexities are the correspondence problems you get. So he's going to draw 3 drawings of a face, and he's got a way of representing those lines as high-dimensional vectors. There's some issue of correspondence. The correspondence problem is across the 2 drawings, mapping the correct high-dimensional vectors to each other. But once he's got that, he basically has a vectorial data set. So that correspondence problem is basically moving the columns around to match up the correct column to each other. He's got 3 data points in probably hundreds of dimensions. Okay, so that's kind of large P, small n. So that's what he's drawn the first drawing already, and he's drawing the second drawing next. And then what he does, he's at this nice little interface they built. So the second drawing, he's putting the eyes up, and I don't know if you can see what the other drawing was like, but he had a triangle mouth, and now he's got an open mouth. When he first does it, he doesn't have the correspondence solved, and that's one of the most interesting bits. It's not interesting in terms of performance, but it's interesting in terms of what the model does when these lines are told to move around the place. So what he's going to do is, once he's done the drawing, he's going to move around in a 2D space here by clicking and moving the mouse. So these are his 3 drawings. So you can interpolate that, right? You guys can see what sort of things this face is going to do. But can a computer? So it's got the correspondence wrong, but it's smooth because it's a Gaussian process. So it's got, you know, okay, like That's great. I love it. So what he does is now he goes in his interface, he can go and tell it which line should be which, and I think that he even has to get the direction right. He's fixing the direction on the nose. But he's generating from X. As he moves in X, he's showing you in Y the high-dimensional vector visualized back as a drawing. Yeah? Does that make sense? Is that clear to everyone? So you're observing Y on this side. Oh, sorry, on this side, sorry. X and Y are on top of each other. X is the background, and now these four drawings are like that. He's just doing a bit more correspondence. And Y is this, yeah? So as he moves, he's just showing you the mean function. As he moves X, the inputs, he's showing you how the mean function changes. Okay, so I think that's kind of impressive. Now there's some things it won't do, so this is outside the regime of the data, right, where he goes down there. So this is his probabilistic stamping tool. So as he stamps, it chooses a random place from the latent space and draws a different face. Or now he's got this idea of click and move to get the face that he wants. So of course he doesn't know anything about constraints, and there's nothing embedded in there. It's entirely driven by a Gaussian process, by observed data, 4 observed data points, which I think is, I believe in this type of way of modeling, and I believe in the recursive dimensionality not existing if you model correctly. This is a nonlinear model, remember, with 4 data points in hundreds of dimensions. And you can do that with Gaussian processes. Now he does it with some insects, so these are a bit more distinct. The interesting thing to happen here, of course, there should be constraints where the legs stick to the body, and what you see if you look closely is the legs move off the body, because those are data-driven constraints, and it doesn't actually have any, yeah, he's got the whole correspondence thing to fix. But it's even interesting when you see that the correspondence is wrong, it's actually moving one line to another. It does it in some sort of reasonable way. Of course, there are many different ways it would try and choose to do it if you were to sample. You're just seeing the mean function. Yeah, you're not seeing, if you were to choose a path between those two, in fact, with Alessandra and Philip and Søren Halberg, maybe Mikhail as well, we're looking at using the geodesics associated with this model to find the shortest path between 2 places, which actually aren't straight lines, and using the sort of techniques that Philip was talking about to solve all the geodesic differential equations. So now he's got this sort of probabilistic stamping tool thing again. Oh, and the best bit at the end is he puts like music on and he makes the insects dance. But of course it doesn't know about the legs joining into the body. So, I mean, that's my favorite application, because it just shows to the max this issue of if you actually have very high dimensional data, you actually become very well determined, 2-dimensional latent space, and you can get these very good human-like sort of, interpolations. Which I think shouldn't be surprising for us that should be possible. I think historically it was surprising because people say, well, look, recursive dimensionality, blah, 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 blah. Yeah, normally this, I could turn the music up, but maybe we should just move on. It makes it dance, yeah, cool. The other thing, I did have these, when I first built these demos, the demos that I would be showing today if I'd sorted them out this morning, you can spend ages with stick figures and whatever you are modeling, making them dance around and stuff like that. Yeah. My ambition is to make an app for the iPhone that makes me a lot of money based on a Gaussian process. I'm sure if I had the time, it would be easily possible. Okay, so people have used these in other domains. I mean, that's oh bugger. That's one of my favorite ones. Oh, define layout. What did I do there? Wow. So people have used them as models of human motion for tracking this model, and people have used them for this assisted animation, is what we've sort of seen. Shape models. There's some really lovely work. Well, Carl-Henrik Eck, my PhD student, and I, we worked hard at this idea of using these models to correlate 2 data sets, so a shared latent space for 2 different views of data. And there's an example of that in the lab, and we've got really nice methodologies for doing that now that work really well. This is a while back. We didn't have all of those methodologies then. When Carl-Henrik and I were working together with Phil Tor, and we're trying to predict pose from silhouette. So a silhouette from, a pose from silhouette. So you've got motion capture data like that of someone's pose, and then you've got a silhouette picture, and you try and predict, given a pose, what their silhouette is, and you relate it all through this reduced dimensionality space. So we kind of got it working and stuff, but maybe we didn't have the right image features. These guys have got really impressive work on taking things like images of cars and then knowing what the shape of the car is, all sorts. And they all do it with GP-LVM. That's Ian Reed, and I can't remember the first author's first name. Victor, I think. Yeah, Victor Priakuri from Oxford. And that's from 2011. So this powerful uncertainty handling of GPs leads to some really surprising properties. And it means that you can end up with these nonlinear models. They can be used with, I mean, I'm not going to show that example, with fewer data points than dimensions without overfitting. And the reason all these traditional ideas of overfitting fall away is certainly if you've got very large, I mean, this is the right domain. And let's just sort of illustrate that again by going back to the difference between these two likelihoods. So I have them up at any point? Or, yeah, this likelihood here is a product over n. So the parameters of, so this is the linear case, reverting to the linear case. W is, as we said at the beginning, I think Q by D, or D by Q, I think, or P by Q, sorry. W is P by Q. So there's PQ parameters in W. So it scales with P. So this idea of large P small n is that as we increase P and don't increase n, W becomes badly determined. Yeah, and that's absolutely the case. Now, the sort of interesting thing with the other model, as we said, is this model here. Better on the next slide, perhaps. This model here is badly determined. This is true for the linear case as well. The uncertainty associated with x is large in the case where you have many n and small p, the large n small p problem. And actually what everyone's been doing for years is if they have large p small n, they solve this one. And if they have large p small n, they solve the other one. So they've been doing the correct Bayesian thing. The correct Bayesian thing is actually to do maximum likelihood for the bit of data which has smaller dimensionality, because you integrate out more variance. What's the Rao-Blackwell theorems? You integrate out the thing of largest dimensionality, all else being equal. So the correct treatment of this model from a Bayesian perspective is to do this dual model when n is smaller than p. And I mean, we've been exploiting this quite a lot because people kind of don't notice this, so we keep secretly noticing it in different domains. So we've looked at EQTL studies, where the EQTL, so EQTL is trying to associate gene expression data with SNPs, so mutations in your genome. And in those type of studies, you may have sort of 1 million SNPs, and then you're trying to predict what the gene expression is. You build linear models, predictive models of the gene expression given the SNPs as inputs. But standard linear regression doesn't work very well because there's a lot of confounders. So people started building these PCA type models. If you've got the probabilistic framework in this model here, you just add the confounders in, right? So you have x becomes split into confounders and SNPs. So part of x is observed and you don't move it, and part of x is a confounder and you've got to deal with it, it's missing. But the traditional approach is integrate over the confounders, we don't know them. But in those domains, your data y has 30,000 values, it's gene expression or something like that. So integrating over the confounders is the wrong thing to do. Integrating over the mapping is the right thing to do, and you end up with an ANOVA-like description of your data. I mean, not sort of, maybe not fully ANOVA-like, but you end up with this a covariance where you get one term which is from these confounders, which we actually call in that paper x transpose, and another term that is from your observed inputs, the SNPs, like a genetic term, SS transpose. And then you can add, Chris Holmes has done really nice work where on models of that type, you then start adding ANOVA-like terms, such as whether they're in the same family or whether they went to the same clinic, and to explain batch effects. It's very trivial to do that in this Gaussian process perspective of adding up different covariates. So that's why I like the interpretability. I think it's totally right what people have been saying earlier, that it's not always clear where the covariance function is coming from. In some cases, it's not always clear what you're saying when you look at the functional form of a particular covariance function. But if you're decomposing your signal into a bunch of components, because these models are additive, it's very clear what you're saying is composing your observed gene expression. And in the case that we augment this with SNP information, we're saying some latent confounders plus some input regressors which are from SNP plus some knowledge about which lab this was done in, plus whatever else we want to put in. It's a very interpretable way of looking at the model, which is something I like. Let's see. So this is the result of the demo that I'm not showing. But it's still a challenge to do what we often want to do in these things, which is estimate the marginal likelihood. So if we don't integrate, so I was a great advocate of stop integrating over x, let's just maximize it. And occasionally people would say, but if I maximize it, then I go, yes, I know that. But that's what we should do, and it works very well. But there are these problems. In particular, how do we select the dimensionality that we choose? We just have to fix Q at the beginning, just as we did with PCA, and then use that dimensionality. And to do that, we need to estimate the marginal likelihood of the associated model with x integrated out. Or we might be in a domain where there is uncertainty about x. In fact, Max Wiesler, when he was doing his MSc project with us, I think that we were working with this model and we were introducing this uncertain variant, and Max is like, well, it's not performing any better. I think in the EQTL studies we were looking at, the Bayesian variant of the model was not performing any better than the standard variant, which was frustrating because it's a reasonable amount of work and it's very elegant and everything. And then suddenly one day I said, oh, I know, you've got to throw away a load of the genes. Because kind of obviously, if you have large P, then the Bayesian approach doesn't help. But if you've only got sort of, now let's not do EQTL studies, which are where you're trying to predict gene expression, this very high dimensional object, let's just try and predict phenotype, so something different in clinical studies, something very low dimensional, then we'll have a lot more uncertainty about what the confounders are, and we want to use that uncertainty. So the sort of follow-up question is, how do you integrate such uncertainty? So we want to now sort of integrate everything out. Now, it's a little bit technical, but the way we can do this, so this is a Gaussian process, and James decomposed the likelihood yesterday into the two terms that make up the Gaussian process, the marginal likelihood, one of which is an expected log likelihood, yeah? One of which is a KL divergence. And we're actually just putting the Gaussian process in here. So if you're going to do a variational approximation, what you need to do is try and fit something of this type. So you're looking to look at an expected log likelihood, and then you're adding a KL divergence between your approximation to the posterior and the true... sorry, no, I'm not even on that one. That's a prior, isn't it? OK, sorry, I'm not even there yet. Let me delete that bit. What we've got here is we've just got a standard decomposition of the log likelihood into two terms. So this one comes about by just pulling the prior out. So I have to check where I go next to remember what that one is. OK. Yeah, I think this one, yeah, I remember what the point of this slide is. So the point of this slide is that this term, which is the KL divergence term, if that's Gaussian and that's Gaussian, this is easy to deal with. What becomes difficult to deal with is this same thing again. This is log of the Gaussian process, expectation under a Gaussian. So we're just back to the same problem of how do we propagate noise through a Gaussian process, which is kind of difficult to do. It's very difficult to do because this expectation Q of x, x appears in k. K is already a nasty nonlinear function, but that's all right, actually. In fact, Jeremy Oakley talked about propagating uncertainty through a GP yesterday, and there are tricks for doing that. You can deal with that nonlinearity. You compute the relevant moments for the exponentiated quadratic. But what you can't deal with is this matrix inverse. That really messes everything up, because that takes all these x's and starts distributing them. It turns the covariance into the precision matrix, which moves all the x's everywhere. So it's sort of been known, I think, pretty much simultaneously. I think was it Tony or Jeremy, but Tony's group, people sort of said, look, we can propagate uncertainty through Gaussian processes. And Rod Murray-Smith's group in Glasgow with Carl Rasmussen, with Kineo Candela, and Agathe Girard also showed the same thing, that you could take the expectation of the mean of a Gaussian process and compute the variance under these Gaussians. That turns out to be tractable. But this inverse is really problematic. And Michalis was Michalis Tsitsias, who we talked about as involving the as deriving this, what I call the collapsed variational bound, but the bound that James introduced yesterday, the variational DTC bound. He was in Manchester when he derived that as my postdoc, and we always also talk about these problems, and he sort of said one day, well, actually, I've worked out how we can do that expectation, we can deal with that inverse. And the whole thing relies on introducing those inducing variables we saw yesterday. So this is just a rewriting of the bound that James wrote yesterday. CI is what we call the trace term, this thing that kept the inducing variables near the data. And this is the approximate, I've not written, the expectation of this f under P of u. When James wrote it, he wrote that fully out as sort of KFU, or he calls it KNM. He wrote it, that expectation is, sorry, this term here, just to get my notation matching. The expectation of f under P of u turns out to be k, in James's notation, KNM, KMM minus 1, u. Sorry, the expectation of u. And James was writing it sort of more in this form. I'm writing it because I don't want to have all those k's there. But remember, this variance here was sigma squared. So x now only appears in KNM. This is an inverse here, it's an inverse KMM, but this inverse was based on z, the location of the inducing variables. And we're not going to put any uncertainty on the locations of the inducing variables, we're only going to put uncertainty on the locations of x. X only appears here. So if we apply this bound that James introduced yesterday, I mean, it's been a real breakthrough, this bound for us, and not just the initial bound, but re-understandings of the bound. We've been thinking about it a lot, as I hope it was clear from James's talk. Suddenly allows us to do this tractably under distributions over both. If we do that, sorry, if I do this integral over u, I can't do this thing tractably because things fall apart again. But if I do this expectation now, so what I want to do is the expectation of this under x. And I can pull that inside this expectation of u and do it before I do the expectation according to u. And it turns out both are then tractable. So that allows us to do both integrals. So I think that's just going through the same thing. So the only term we then need to deal with additionally are these expectations of the trace term, which I think there's no problem with them as well, because we just have this diagonal bit to deal with. So what turns out is we need these moments of the covariance function. So the expectation of this under x and also the trace term requires that we end up needing expectations of k and m under q of x. So the whole thing becomes tractable because of that. Now, that's not tractable for all covariance functions, but it is tractable for the exponentiated quadratic. So in the lab, you'll implement this model, or you'll run this model, and it will be with an exponentiated quadratic covariance. It's also tractable for the linear covariance, so you can do like a Bayesian nonlinear dimensionality reduction, Bayesian linear dimensionality reduction model. And one of my students, Max, has been working a lot on those sort of models. Okay, so I don't want to go through all the details of what this then means as well, and this is really where a lot of our new directions are going, is we can start to do things like quite complex priors over latent spaces. So this all works for Gaussian priors. But my immediate sort of thought, and in fact we have a model like this, is you could put a Gaussian process prior over X. So what you can start doing is stacking these models. So each of those things is a Gaussian process, some sort of regression. But you could do, so one of the things we do, the simplest prior we look at, is a sort of prior where this is like a linear regression variant because this is one output. In linear regression, people do something called ARD, and that will be mentioned in the lab. In ARD, you've got these 6 inputs that are going to generate your data, and you might believe that one or more of these inputs is less relevant than another. And in fact, also Jeremy used, they don't call it ARD, they just talk about separate smoothness parameters for each input. We'd call it a length scale. We can scale each of these inputs and have a parameter associated with that, and we can optimize that type of parameter, thereby learning the dimensionality of the latent space. So we go from a shared prior over over X. So there's 2 ways of looking at this actually. You can either think of it as scaling W, because X and W always appear as an inner product. And we've seen that already. So if you put a prior over X that has a scale, equivalently you can put a prior over W that has a scale in a latent variable. You're just moving the scale between the 2 variables because it's unidentifiable. So in this case, I'm kind of thinking of it as a prior over the latent space, and what you can make is that you can make that a diagonal covariance prior. So you've got separate Gaussian priors over each variable, and then what actually happens if you run the model long enough, which unfortunately can be a long time because it's not super fast, it actually just switches out. It reduces the prior variance to 0 and takes out nodes completely with enough optimization. When it's numerically stable enough, it takes quite a lot of work to get it numerically stable. So in a nonlinear case, you can do the same thing. And in the nonlinear case, because of these equivalencies, what you often do is you might put this diagonal term down in the A matrix. And that's what Jeremy was doing, although he was writing it underneath in a slightly different notation. And we call that an ARD prior. So it's equivalent. It doesn't matter. In fact, I like to flip between the views. It doesn't matter whether you put in the Gaussian prior on sorry, it is W here, isn't it? On W or X, it's the same thing. So did I actually? That slide's illustrating that, isn't it? Yeah. So it's the same thing, right? So those 2 things are equivalent. Okay? So once you've accepted that you can do priors on X and do interesting things, that's a very simple one. We can do dynamical priors. So something we do, people are interested in like Kalman filter models, which as we saw yesterday is some sort of dynamical prior followed by a linear mapping. Well, if you want a nonlinear Kalman filter model, you just have to take this model and put a dynamical prior on the latent space. That could be a standard Kalman filter prior, or it could be a more involved Gaussian process. So that's something that the first people to do with a map solution, and they did it autoregressively, so it really was a nonlinear generalization of a sort of Kalman filter. Jack Wang and Aaron Hertzman and David Fleet at Toronto did, and then we did it more recently with the fully Bayesian approach that allowed us to learn the parameters of the prior as well with my student Andreas Damianu. Structured learning prior, this is something we're using a lot. This is so I have slides on that perhaps, where we're trying to share information between 2 data sets, and there's a little example at the end. So people may have heard of canonical correlates analysis. I never remember. CCA. It's also invented by Hotelling, so he liked inventing names with C's in. Now in CCA, what you do is you have some latent space. The probabilistic perspective on it would be that you've got 2 data sets. It might be pose and... did I go on the Y the wrong way around there? No. No, I have. Okay. It might be opposite way around Y's. That's very weird. So you might want to try and relate these two data sets. So it could be, people have looked at English language, French language, trying to relate them with a shared latent space. But if you just put a shared latent space on, this has to explain everything in both sides. So CCA actually has a noise model that is a full covariance Gaussian. So it's got a, CCA can be seen as like this XX transpose plus sigma 0, 0, sigma 1, sigma 2. Again, models are so easy to understand when you've got the covariance structure. It's saying, please give me, I'm happy to explain within a class what's going on for that class with this sigma covariance. That's full rank, fully parameterized. But for the cross covariance between the classes, I want you to explain that in X. Yeah? Does that make sense? So that seems nice, but then you're sort of having a low rank effect here. I don't think it was derived like this, although it was her telling derivation, but it's been reinterpreted like this. What if you want this thing to be low rank? Well, again, it's easy to write down the model for that because you're just adding some low rank things, and all you get is a Z1 on the left-hand side and a Z2 on the right-hand side. So now what you're saying is that my data has some shared information in X and some private information in a latent space that's just for that data. So why is that interesting? Imagine things like silhouette and pose. So with a given silhouette, it isn't fully determinant of the pose. Because if you see me my silhouette that way round, or that way round, it's ambiguous if it's just a black outline which way round I am. Or if you see that silhouette, or that silhouette. In fact, we worked extensively on a data set of silhouette on pose, and we were really curious as to why there were no ambiguities until one of us noticed that the guy's left arm was always sticking out. So, yeah, that took a long time to realize that. So the data set had been generated in such a way that that ambiguity wasn't there. But normally there's these ambiguities. So the information about pose, in order to specify pose, you need extra information. And in that case, the idea is in here, you would store which way the guy is facing. In order to create the pose, and the silhouette only tells you that he's either facing forward or backwards. So you put different bits of information in here. But when I was looking at this, and I should say Sami Kaski's group is also with Arto Kalami. They look at models like this, linear models like this, which they have really they've done a lot of work on canonical correlates analysis as linear Gaussian models, historic approaches to this. They've got a great JMLR article on that. So they've been looking at similar things. And this is often very interesting for different views of a patient or a gene expression data set, to try and correlate which things are correlated and which things have their own special governing noise. So you can easily do this with this modeling setup by just putting the right prior on these latent spaces. So you just take these two data sets and you have shared latent spaces across the data sets, but each data set has a different set of parameters. So in effect, the way, one interpretation of what we do, it wasn't the one that led us to do it, but I think it's a nice way of looking at it. We have a shared latent space for describing pose and silhouette, but we have diagonal covariance Gaussians as priors on this latent space that are different according to whether you're pose or silhouette. And what happens in practice is pose ends up deciding it wants that prior, and silhouette ends up deciding it wants that prior, and they also end up switching off. So they end up choosing some directions that are just interesting for them, and then they have some other directions where they end up with a more spherical prior. So once you've got this sort of probabilistic framework and you want to start pulling these data sets together, it becomes really clear. Well, good ways of doing it become clear. It's not always clear they're going to work, but this one, this manifold relevance determination from Andreas Damianu turns out to work really well. And a lot of credit for that area. I mean, this paper was key. I kind of couldn't quite believe it when Michalis spotted that we could do that. And there's a large amount of work going on in the group to expand these models to large data sets and apply them in various domains at the moment. So I think that's the last, or the second last example. The last example in the lab this afternoon is one that you need to run on a standalone machine because it's an interactive example. It won't work on the web browser, but it's just there in the lab. But the last example you can run on the web browser is on this manifold relevance determination. It's a toy problem, but it'll give you the idea. So, any questions? Well,
you sort of started out by talking about factor analysis, which to me, anyway, means typically discrete factors.
No, originally it was always continuous. Things like IQ.
Okay, but
yeah, it could be discrete. Yeah,
they're typically largely discrete factors.
You work with sociologists on factor analysis stuff at some point. Yeah.
Yeah.
So you sort of had a revisiting in Philip's thesis. He was revisiting it, and it's moved quite a long way away from factor analysis now, isn't it? These sort of sociological models.
Well, although actually, I think they still use these. There's a small set of standard factors that are very popular in this area. I think it's mostly because the whole community has built on them. They've become they've become the standard way of talking about patients. For example, there's this big 5 model: openness, conscientiousness, extraversion, agreeableness. And that is based on a factor analysis model that was done in the early 20th century.
Yeah, but I think you were saying that people have even kind of forgot of what its origin sort of was. It's sort of it's now a thing. It's so embedded.
Sorry, I'm not mean the factors being discrete. I mean the data.
The data. Sorry, right. Yeah.
So you're setting up a.
Right. So yeah, of course, yeah.
A probabilistic description, which is essentially a Gaussian description of Y there.
Yeah.
Yeah.
So you can just take.
If our data is naturally discrete.
Good question, because that's really. A lot of the data we want to deal with is like that. And Ricardo has a paper in submission. In fact, the work Ricardo showed earlier about doing DTC, EP-DTC yesterday, and EP-FITC, from our perspective, is driven by a need to get these models working with non-Gaussian data in a practical way. So although they work for classification or whatever else in general data, one of the needs is to actually work with these models with non-Gaussian data. So we want to be very careful about the likelihood when we incorporate information. I mean, the ambition is to do these latent variable models when you've got massive missing data. So you can imagine the doctor wants to see the patient characterized in some fixed dimensional space. Loosely speaking, we're not working with any clinicians. This is our model of a doctor. Our simple spherical model of a doctor says that he wants to see, he characterizes the patient as living in some low dimensional space, but it's a fixed dimensional space. But perhaps he's uncertain about where they sit on that. And he may be uncertain because they haven't done many tests yet. So we need to have uncertainties over that space, and we need to be able to assimilate whatever range of tests anyone has. And you can easily do that in these type of models. The mathematical formalism for doing that is clear. And so we're very keen on doing that and sort of actively working. It does add to some computational headaches, but this new method that James is, I think, going to speak tomorrow about at the workshop, Gaussian process for big data, may re-alleviate those computational headaches and allow us to push forward with doing very large, massively missing data, sparse data sets in this modeling framework. Sorry, that was a long answer for a short question.
No, so it's on the menu.
It's actively being consumed. We haven't had the coffee yet. But it's actively being consumed. So we have implementations. The code does that. I don't think we spend a lot of time testing, but in fact I haven't looked carefully at the code. But the way we plug the code together as these things work. So I'm trying to see, Max. Does the code currently allow us to combine the release code, non-Gaussian likelihoods with these latent variable models? I think
theoretically, but it's very unstable.
Yes, theoretically, yeah. It's as I say, it's being actively consumed. But it's stuff we're trying to get out in the code. Yeah. Theoretically, that's a good way of putting it. The code theoretically does that, but when you actually press return.
Works, but you have to
code is one of those things where I suppose it's identical in theory and practice, isn't it? I mean, one of the few things. Sorry, other questions? Owen.
May not have vast amounts to do with what you've talked about so far, but if you're interested in supervised dimensionality reduction, what GPUs have to offer?
Oh, lots of things. And again, it's one of the, it's a generic, in machine learning, this happens a lot, that we get fields that call themselves something like multitask learning, supervised dimensionality reduction. I don't know, what are other examples of fields? Multi-view learning. Structural output prediction. Philip was giving examples of this earlier. Which, if you do things probabilistically, it's just like understanding the structure of your data and implementing it in your model, I think. So they're not very buzz terms. I think if you go to ICML, I particularly noticed this when it was in Edinburgh, you had all these sessions where people were talking about multitask kernels, and then you had someone else talking about semi-supervised learning, and then parallel to it all, there was this probabilistic modeling session where everyone talked about all those things, but totally separately from the people that weren't doing it probabilistically, which I think is probably not a good thing. I suddenly realized that and thought, that's not good. So supervised dimensionality reduction, people, I think they think about it algorithmically. From a modeling perspective, we could look at it in various ways. We could observe an additional output from the latent space that was the class label, but treat it with different parameters. And we actively have been doing that. So this MRD model I talked about here, what we've been doing with that is saying, well, have this label coming out here. And a particular interest is doing this for survival analysis. Joint work with sort of Aki Fatari and stuff that Alan Saul, who's done so much to set this up, has been looking at. So let's imagine that we've got some high-dimensional data about the lipids in someone's blood, and we've got information about their cardiac survival. But the traditional thing, and Aki's got models that do this, is to map from Gaussian process survival modeling, he does. So you map directly from the lipids to the Gaussian process and maybe try and do some feature selection. I won't say we've got this working well yet, but one of the theories we have is, well, maybe it's better to go through a low-dimensional space, learn the sort of manifold of how people's lipids are, and then predict from that space out to a survival thing. Now, there's some problems with that, and you remove this private space because you don't allow the survival. You force the survival to share information with the lipids. So the idea is, in some sense, I mean, this could even be a linear model coming out here. In some sense, this chooses a linear direction of it forces these latent spaces to orientate along the survival information, but it could equally be class information. Now, in practice, you do get a problem, one of those annoying problems that happen because your model isn't correct. Even though this model is very powerful, it's clear that it's not capable of modeling the full complexity of this data. And this data is often continuous and high-dimensional. So the number of bits you lose by mismodeling something become very, very large. And if you've got a single binary label and you choose to ignore it, the number of bits you lose is 1. So very often the performance is poor because it's a unsupervised model and it spends too much time dealing with that. So we do nasty things like ramp up this likelihood term to force it to pay attention. And that sort of seems to work. But you can imagine doing, Raquel Urtasun has done work where she's put priors on here that are derived from the label. So you have, it's not a mixture prior that she uses, but it's that type of thing. You force, I think she uses like a Rayleigh quotient type term to force the latent data apart according to class, and that seemed to work. Frustratingly, there was some evidence in the field that this worked better than pure Gaussian process classification for small data sets in certain circumstances. When we recreated those experiments carefully, it didn't. It worked worse. And that was really frustrating because a lot of our work in this direction was based on those results. But I think that they didn't initialize their kernel parameters very well. There are lots of other ways you can envisage doing it within this model. I don't think there's just one way. I mean, you could, yeah. But does that answer the question again? Very long answer. Dan.
There's no lunch yet, so.
Oh, keep going. All right, that's right. It's easy. Yeah. Dan, no lunch yet. Don't worry, you're not missing.
Really long question. No, but related to that a little bit, I was wondering about using this approach for clustering in the latent space.
Yeah.
And so you've got your latent space is really, you're treating it as your prior is Gaussian, so maybe it doesn't make sense, or
really nice question, and something that leads me to give you another talk. Sorry, I've just found out lunch isn't here. So that relates to something, I always feel when you organize these things, you have to be a bit careful. What is that, my talks page? You have to be a bit careful about spending too much time focusing on things I'd give as a research talk, because it's sort of a privilege to organize these things. If I spent the whole time talking about my latest research, I would feel that would be abuse of privilege, although I'm happy for other people to do it because that's why they're invited. So it relates to something. So okay, what's going on here is this is a model that we're working on actively now that I think is very important for these data as well, and it relates to your question. This is a deep Gaussian process model. So you have a load of unobserved latent variables. You start Gaussian process latent space to Gaussian process prior over another one, Gaussian process prior over another one, Gaussian process prior over another one. And the idea here is you might have observations which are more associated. Up here, things are supposed to be more abstract. There's all this deep learning stuff going on. I do buy into that structure of model, totally, and have for a long time, but it's difficult to see how to do it with Gaussian processes. But this approach of Michaelis allows us to do it, and that's what Andreas has been working on. So up here, the idea is that these features are broad and abstract, and these features become more focused. Now, your question was really astute to something that took us a while to notice, and I wanted to bring up this plot. I told you I could talk forever. Oh, so these are results on these sort of shared models that Andreas also did. Here, this was interesting. So we did these models of digits, and our interest was how many layers of Gaussian process models did we need to model a digit? Because this one-layer nonlinear dimensionality reduction model is quite a powerful model. So you might think, what are you doing putting extra stuff on? Now, very quickly, it does not add to the complexity of the model. If you think about it, every time you add a layer, it's constraining. The most overfitting case is actually the case where you have one layer, because everything can operate independently. As you put another prior on top, you're forcing things to correlate. All backstory to answering the question. What we found was, in this case, that we needed 5 layers to model a very small data set of digits in order to get the best bound on the marginal likelihood, so we can compare these bounds. And what we find is at these top layers, the features are very broad, switching between digit, and the low layers, they're sort of switching in. So here, this is a feature which switches in and out the top of a 0. So that's what we hope to find. That's what the big story about these models is. But what we were surprised us was, we're getting the best performance in terms of digit classification, where we do one nearest neighbor errors. So it's unsupervised, but then we see how are you doing, give your one nearest neighbor error at this level, not this level. Scratching our heads a bit about that, until of course you realize that the prior at this level is Gaussian. And if you look at one of the reasons it gets such a good probability is it makes it Gaussian at the top. And the much better model in terms of separating the digits is the mapping of the Gaussian through a Gaussian process that now gives you a sort of structured non-parametric clustering model. All the digits move apart, and then the classification error is much better. So but we haven't done specific experiments in that domain. As I said, long answer, but they said lunch wasn't here. The non-parametric clustering model was very, very useful in improving the model of the data. So it almost feels like whatever's going on at the top is just going to be, first of all, a prior, which is a very flexible, broad, non-parametric clustering prior, because the Gaussian prior isn't very good if you want to separate these things, which may be another reason why we're not getting very good results on the supervised dimensionality reduction, because it's trying to pull the data together in some sense. Yeah. The fact it doesn't is actually, again, because it gains more bits by modeling the data correctly rather than making the data Gaussian. But when this shows you that you have to get quite complex to start really modeling your data in such a way that it's happy to make the prior correct. It's bizarre when you think about it. I mean, that PCA example I showed you at the beginning, I mean, we never expect the result of PCA to be a Gaussian, do we? It never is. But that was our prior. And it's because the model's never capable of making it so. It's never capable of modeling the data in the correct way. So retrospectively, when you think about it, unless your data is Gaussian at the top layer, it's so you're absolutely right. If you wanted to cluster it, you could do mixes of Gaussians. And I think that would be possible. Is the food actually here now? Or it's been laid out. Well, I'm happy. Other questions or about anything else for any of the other speakers? Owen?
This. Learning hyperparameters for deep nets is meant to be a bit of a dark art, right? Is this any less true for well,
initializing these models is difficult. But in this model, there's one parameter per latent dimension, pretty much, order. There's a couple of other parameters. It's kind of straightforward. And everything's being integrated out, the latent variables and the mappings. The challenge is scaling it up to millions of data, which is what we're looking at now. This can only do thousands of data. I think Zubin has work on some deep models where you can estimate the evidence. And I think that's the only other work I know of. In their work, they found that they couldn't, under the evidence, justify a deep model. And in our work, we found we could. In fact, we tried only up to 5-layer models in the first case. We do get issues with the parameters switching off inside local minima. Richard Turner has a nice explanation of why this sort of thing can happen in variational methods. Because, again, you gain a number of bits or nats by matching your prior. So you should never initialize near your prior, because that's always some sort of local minima. And one of the things that can happen is it can aim for the prior, if it's close to it. And in this model, what that means is if you're getting this right, and once you've got that prior right, the best way of getting that prior right is to disconnect this from this. And then you get pure Gaussian here because it doesn't have to worry about data. And then everyone gets to do it because that mapping becomes white noise, and this one's Gaussian. So and Rich actually said that to me after, I think, maybe this talk, that may be what's going on, and I think he's totally right. And you have to be really careful that very often you're too close to the prior and everything goes back to the prior and it switches layers off. But if you initialize it carefully, you get a better bound on the likelihood by having those layers back in.
Yep.
Is it there? Okay, I'm getting a signal. So, okay, I'm just hearing. So it sounds like food's ready. So I've already overrun. So if there's no further questions, today's special lunch. It's a Moroccan lunch through some contact, cash in hand, that sort of thing. So hopefully, because we thought 3 days of university catering food might be a bit much, so special celebratory lunch. And maybe before we take the lunch, I should have thought about this. Well, I think we should do a photo in the rain. Is it raining? Can we? Maybe should we do it after lunch? It's a bit harder to organise. We'll do it after lunch. We'll do a photo outside after lunch. Maybe it's a bit less damp. Okay. So lunchtime.